Hello, am I audible? Hello. Hello. So we will wait till 6:05 and then we will start this session. I hope my screen is visible to all of you. Hello all. Uh, Welcome to the extra session of solid mechanics session. So my name is Manoj Shikhar. I'm a PMRF scholar at IIT Delhi. Uh, I work under Professor Ajit Kumar at IIT Delhi and I am a PhD scholar in the Department of Applied Mechanics. More about me, I have done my BTech and MTech from IIT Kharagpur. And today is the last session for this course. I will be trying to solve some numerical problems here. Before that, we will just go through the topics that what has been covered in this course. And I will take up few problems, numerical problems mostly, because we have done a lot of theoretical problems in the class already, the previous lectures. So, this subject, it actually dealt with many new concepts. For example, we started with the working of vectors and working with vectors and tensors. Then we discussed about like the what is traction vector, what is stress tensor, what is the matrix representation of this tensor. Then we looked at the transformation of the stress matrix. We discussed stress equilibrium equations, the balance of linear and angular momentum balance equation. So basically balance of linear and angular momentum. Then we went on to discuss that what are the principal planes, what are the principal stress components, and how to maximize the shear component of traction. Then a new topic, the graphical representation was discussed with, which is called Mohr circle. We saw what are stress invariants, how can we decompose the stress tensor into hydrostatic part and levatoric part. After that, we moved on about what is strain tensor, what are longitudinal strains, what are shear strains, what are local volumetric strains. Then we discussed the Mohr circle for strain tensor, strain invariants, strain compatibility conditions. Then we realized that the number of variables we had were more than the number of equations we had. So we discussed the stress strain relation, also known as constitutive law. Then we saw two different kinds of stress strain relation. One was linear relation for anisotropic materials, then the relation for isotropic materials. And in this course, we mainly dealt with isotropic materials. Then we found out that we need to introduce the cylindrical coordinate system for some of the problems, so that our problem statement can be made simple. Okay. So we discussed the linear momentum balance in cylindrical coordinate system. We discussed our strain matrix in the cylindrical coordinate system. Then we moved on to discuss the extension, torsion, inflation in a hollow cylinder. After that, we moved on for the bending of beams. In that, first we considered that pure bending of beams, then non-uniform bending of beams. In pure bending, only the bending moment was applied. In non-uniform bending of beams, along with the bending moment, we also had transverse loading. Then we thought that what will happen if the cross-section of beam is not symmetrical, if the beam is unsymmetrical. Then concept of shear center was discussed. And after that, we discussed two theories of beams, Euler-Bernoulli beams and Timoshenko beams. And we also saw what is a beam buckling. Then energy methods was discussed to solve a few problems, like to find the displacement or to find the load at a point. And in the last lectures, we discussed the theory of failure. So this was the outline of course which we went through in past 3-4 months. Now, all these notes, all the notes of these video lectures are available at the website mentioned on this slide. Okay, so you can go and download the PDF notes. At the end of the PDF notes, you will find some problems. If you solve those problems, you will find that the similar kind of problem or a part of those problems are being asked in competitive exams like GATE or ESE. or any other examination you are preparing for, in which mechanical engineering is a subject. Okay. Or even in civil engineering, this subject solid mechanics is taught in mining engineering also. So for those topics. So this was the recapitulation, and today is the last class. So I wanted to discuss a few numericals. Uh, so let's start this session, and I try to cover as many questions as I can. So so the first question is, prismatic bar of sides prismatic bar of sides 40 mm cross 30 mm is axially loaded by a compressive force of 18 kilonewton. Compressive force of 80 kilonewton. Question is, determine the stresses acting on an element which makes an angle of 30° with vertical plane. Also find the maximum shear stress value in the bar. This is our question. So basically they have given us a bar. And they have given us that a force of 80 kilonewton is applied here. This is a compressive force, as you can see. Now this dimension is 40 and 30. And here they are telling that we have an element which makes an angle 30° with the vertical plane. Okay. So first we will start with the area of cross section. So area of cross section is 40 into 30 into 10 power minus 6 meters square. So this is 1.2 into 10 power minus 3 meters square. So this is A. Now normal stress on 30° inclined plane. Okay. So we can directly use the formula sigma equal to P by A cos square theta here. And the value of theta is 30°. So P is minus 80 into 10 power 3 Newton divided by 1.2 into 10 power minus 3 into cos square 30. So our sigma will be minus 80 upon 1.2 into 10 power 6 into 3 upon 4. So this is 5 into 10 power 7 pascals with a negative sign because it was a compressive load. So our sigma is minus 50 MPa. So this is the normal stress. Okay. Now we have to find shear stress. So shear stress on 30° inclined plane. We can use the formula tau equal to minus P by A sin theta cos theta. So these formulas, they have been derived in the classes also, in the previous classes. So if you go and you can see this stress transformation formula there, if you put the values of sigma 1, sigma 2, sigma 3 and whatever it is, you will come to this formula. Because here if I see this plane, the stress on this plane will be minus 80 upon this area. Right. So you know what is sigma x now. So accordingly you will have to put there. So I'm directly using the formulas because I'm assuming that in previous classes we have discussed this and you know that these formulas exist. Anyway, so here I will put everything minus 80 on into 10 power 3, 1.2 upon 10 power minus 3 into sine 30 to cos 30. So if we do the calculations here, we will get tau equal to minus 28.9 MPa. Oh, sorry, plus 28. Now let's find what will be the normal stress on 120-degree. Anyway, so we have found out what is the value of stress on the 30-degree plane. Now we have to find like what is the maximum stress, shear stress in the bar. The maximum shear stress is so how do we find that what will be the maximum shear stress in the bar? So there are multiple methods. I can directly write the formula here, but I'd like to say one thing that because this is a 2D thing, right? So we need sigma x and sigma y kind of thing to use the transformation. So if you remember, for example, if we have found something on 30-degree plane, for example, this is a 30-degree. So this will be 120-degree, right? This is 120-degree. This plane is at 120-degree from vertical axis. If this is our vertical axis, this plane is at 30-degree. This plane is at 30-degree from the vertical axis. And this plane, the bottom plane, I will like mark it as some other color, with some other color, maybe black color. This plane is at 120-degree from the vertical axis. So we will have to find what is the shear stress and the normal stress on these planes. Okay. And why do we need to find this? Because in the question they have given us that determine the stresses acting on an element which makes an angle 30-degree with the vertical plane. So we have found the stresses on this plane, this red plane, but other stresses are also acting on this element. So if I draw the diagram here, so it will be something like this. Normal stresses on these planes, normal stresses on these planes. Okay, and then there will be shear stresses here. So how do we find these stresses on 120-degree plane? We use the same formulas, but for theta, we will put 120-degree. So let's do that quickly. Sigma on 120-degree plane equal to P by A cos square theta. So P by A cos square 120. And this will give you the value of minus 16.67 ampere. Now, tau on 120-degree plane. We will use the formula minus P by A sin theta cos theta. And here you will put sin theta cos theta as sin 120 and cos 120. So here we will get the result minus 28.9 ampere. So depending upon the sign of this tau, we decide if it is clockwise or counterclockwise, right? So here the sign is positive. So this is counterclockwise. So on the 30-degree plane, this is the 30-degree plane. 30-degree. So this plane, this is the 30-degree plane. Our tau is in counterclockwise direction. And here you see we have gotten minus 28.9 MPa. So this is clockwise direction, right? Clockwise. That's why I have shown it in the clockwise direction here. Now for maximum shear stress in the bar. If you remember from the principal stress concept, the maximum shear stress happens at the 45 degree from the principal direction, right? So, so if you do if you do the analysis of this bar, you will realize that uh, the if if we are taking an area which is at an angle 0 degree with the vertical plane, so the vertical facing this area, so this will be one of the principal direction. Like the x-axis itself will be one of the principal directions, right? So here theta will be 45 degree. You can do the analysis also. You will realize that for theta equal to 45 degree, you will get the maximum value. So tau max is minus p by a sine theta cos theta, right? So minus 80 into 10 power 3 upon 1.2 into 10 power minus 3 into sine 45 cos 45. So always remember in principal stress chapter, we have read that the shear stress will be maximum on a plane which is at 45 degree with principal plane, right? So always remember this thing that 45 degree is with principal plane. It is not with any rectangular Cartesian coordinate you have taken. So keep that in mind. In this case, the horizontal axis itself was normal to one of the principal planes. So that's why we have put 45 degree directly. Okay, so keep that in mind. So if you calculate this, this will be equal to 33.3 MPa. And it could be on like both 45 degree and 105 degrees. So 135 degrees. So plus minus 35 MPa. The stress of stress, suppose initial stress of stress would have been sigma x 0, 0, 0, 0. Since it is a 2D, so there will be only two. Let's. So this is sigma x. This is x and y. I'm assuming that this is x and this is y. So you can see that on this plane, we have only sigma x and all the shear stresses are 0. So this plane itself is a principal plane. So with this, with the shear stress, with this, the plane which makes an angle of 45 degree will have the maximum shear stress component. Okay. So this was our question number 1. Now let's do a question. Maybe I will do something. Now let's move on to stepped bars. Okay. So the question is, consider a rod ABC. Hello. Huh? Consider a rod ABC with part AB. So this is aluminum and part BC, and this is made up of steel. Okay. Having diameters 25 mm and 50 mm respectively. Now the question is determine the deflection at point A and B. And this is the figure they have given. So this is A, this is B, and this is C. And the loading is here they are applying 25 kilonewton. Here they are applying 10 kilonewton. Okay. This length is 0.4 meters. This is 0.5 meters. Also, for the above part, they have given E equal to 70 GPa. Generally, in questions, they will give you the E of steel and E of aluminium. And for steel, it is 200 GPa. So this is the question. Now, first step is, and this question has been asked in GATE also many times. So the first step is to draw the free body diagram. So when you draw the free body diagram for AB, you will find that there is a compressive loading on AB for of 10 kilonewton. Okay. And on BC, there's a compressive loading of 35 kilonewton. Okay. So this is BC. So if we find the individual displacements of AB and BC, we will be able to use the superposition theorem and we can find the total displacement, right? So, since BC is at the bottom of this rod ABC, first we have to find that how much this BC is moving. Okay, so the deflection of part BC is the load on BC, PBC into LBC, the length of BC divided by area of BC and the Young's modulus of BC. Okay, so this is basically PL by AE, but here E and area are varying, length is varying, even the load is varying. So we are writing P, BC, LBC, ABC, and EBC. So start putting everything. So the compressive loading is there. So minus sign will be there with the load. So minus 35 into 10 power 3. The length is 0.5 meters. Area is we can use the pi like pi d square by 4 formula. So pi into 50 square Now the unit is given in mm, so there will be a multiplication of 10 to the power minus 6 divided by 4 into 200 into 10 to the power 9. Okay. So if we solve that, we will find that the value we are getting is minus 0.0446 into 10 power minus 3 meters. So delta BC is basically minus 0.0446 millimeters. Okay. So this is the deflection of point B. Okay. So this is the, because the C point is not moving. Its displacement is 0. So whatever displacement is happening in this part, it is happening in part BC. It will be the deflection of BC. So deflection of point B. So we can directly write deflection of point B equal to deflection of point B equal to minus 0.0446 mm. Now we first find that what is the total deflection of part AB. Okay, so deflection of part AB. We can use the formula PAB LAB upon AAB into EAB. So the load on the on this AB part is minus 10 kilonewton because it's a compressive load. So minus 10 into 10 power 3. The length is 0.4 meters and the area is pi by 4 into 25 mm square. So 25 square into 10 power minus 6. And the Young's modulus is 70 GPa. So delta AB is basically, if you do the calculations, it will be minus point. This is minus 0.1164 mm. Okay. Now here is the tricky part. For the part BC, since point C was not moving. Okay. Since this point C was not moving, uh, the deflection of B was whatever is the deflection in this member. But for point A, the total deflection will be what? The amount B has moved plus the amount AB has deflected. Because in this case, both the beams are getting contracted. Okay, so that's why the total deflection of A will be deflection of, I would have used vector also, but I don't know if that will confuse you all. So deflection of point A is delta BC plus delta AB equal to minus 0.0446 mm plus minus 0.1164 mm. So this will come out to be minus 0.161 mm. Anyway, so this question is done. Now, let's do another problem of similar kind. So the question is, a mild steel bar of mild steel bar is 40 centimeter long. The lengths of part AB and BC are 20 centimeter each. It is loaded as shown in figure below. Okay. Find the ratio of the stresses sigma 1 in AB and sigma 2 in BC. Okay. And they have given take P1 and P2 are the loads. So P1 equal to 1000 kg and P2 equal to 1000 kg also. So P1 and P2 equal to 1000 kg. So the figure is something like this. So they're both made up of steel, and this is 0.2. This is 0.2. Here the diameter is 1. Maybe I should first draw the loads. Then. So the loads are here they have applied P2. Here they've applied P1. Okay. Its diameter here is 2 centimeter. For this, diameter is 1 centimeter. This height is given, this length is given 0.2 meters. This is also 0.2 meters. So, and this is A, B, C. So we can start again by drawing the free body diagram. Okay. So free body diagram will be for BC. For BC, this is P2 and this is P2. For AB, this will be P1 plus P2. And similarly here, this will be P1 plus P2. So we can find the stress. So stress in AB. Sigma AB equal to P1 plus P2 upon AAB. So this is 1000 plus 1000 into gravity. Okay. Maybe I should write Newton here, though they have given the load in kg, so we can also assume kg only. So because they have asked for a ratio, so it's okay. Pi by 4 into DAB square. Okay, so we have 4 by pi into 2000 upon DAB square. Stress in BC is sigma 2 equal to sigma BC equal to P2 upon ABC. So this is 1000 upon pi by 4 into DBC square. So this is basically 4 by pi into 1000 upon dBc square. So this was sigma 1. So we have to find sigma 1 upon sigma 2. So this will give us 4 by pi into 2000 upon 2 square divided by 4 by pi into 1000 by 1 square. This is basically 1 by 2. So sigma 1 by sigma 2 is 1 by 2. Now another question. A rigid bar is suspended by a spring as shown in the figures. Determine the deflection of point B. And the figure is something like this. The spring constant is 5 Newton per millimeter. Here the length is L. This is also L. And this point is B. This point is C. This point is A. So what we can do is we can first draw the free body diagram. So the free body diagram will be at A, we will have some reactions. Let's see, we have a load P1. So, and there is one more load here, okay? So at point B, there is one more loading here. And this load is of 500 Newton. So at B, we have 500 Newton load. So we can do the moment balance about point A. And here actually this is the pin joint. So pin joint will not offer any moment. So this is wrong. Here, this is a pin joint. There is a pin joint. So only reactions are there. So we can do the moment balance about point A because that is the there we have unknowns R1 and R2. So we don't want to consider the moments because of them. So summation of moment about point A will be 0 because of pin joint, right? At A. So this will be P1 into L minus, and I'm assuming counterclockwise as positive, minus 500 into 2L equal to 0. So from here we get that P1 equal to 500 into 2, that is 1000 Newton. Now we know that for a spring, for a linear spring, K into delta equal to force. So K into delta equal to P1. So from here we will have delta equal to P1 upon K. So that is 1000 upon 5 millimeters. So this is 200 mm. Sorry. Actually, here the spring constant is 50 Newton meter. I wrote 5. So the deflection is of 20 mm. Okay. So now we know that this is delta C, actually the deflection of point C. So K into delta C will be 20 mm. Now we can use the similarity of triangles. Okay. Other So this is length L. And this is length L. So from similarity of triangles, delta B upon AB equal to delta C upon AC. So from here we get that delta B equal to AB upon AC into delta C. So delta B is 2 times delta C. So that is 2 into 20 mm. That is 40 mm. So here it was a beam, it was a rod. That's why we were able to do this. In case of beams, we needed to calculate by using the formulas there. Okay. So in rod, we can directly do this. Other way could be that you find the slope of this line. So you can find the equation of this line. This line will be something y equal to mx plus c. I will just write another method. You can try it yourself. Another method. Y equal to mx plus c, where m will be your tan theta. Okay. So y equal to delta c upon AC x plus c. C is some constant. So let me show you only. So suppose this is your x-axis. So at x equal to 0, y equal to 0, because A is fixed, right? It is a pinned joint, so A cannot move. So from here you will get C equal to 0. Let us say this is C1, so that so y equal to delta C upon AC into x. If you don't want to use the similarity, then you can use this formula. Now you have to find the deflection at B. So B is where B is at x equal to L by 2L. So at x equal to 2L, y equal to delta B. So put it there. Delta B equal to delta C upon AC into 2L. Or basically this length is AB, right? This is AB. So this is again delta C upon delta C into 2. So this will be 2 into 20 mm. This will give you 40 mm. So you can use any of these methods. Similarity is much easier, but here also we are essentially doing the same thing. So hopefully these questions are making sense to you now. Now let's do one problem based on thermoelasticity. So the formula in thermoelasticity is epsilon equal to alpha delta T. Okay. Delta L equal to alpha L into delta T. So these two formulas are mainly used in thermoelasticity. Then using these formulas, you can find this stress by multiplying E into epsilon and so on. Okay. So the question is, a bar is free to expand a bar is free to expand. Its length is L naught. And they've given alpha equal to alpha 5, something 5. Okay. 5 per degree centigrade. Oh, no, not 5. This should be small actually. There is some 5 into 10 power minus 3 per degree centigrade. Okay. And they are asking, and they have given E equal to something 200 GPa. They're asking find the strain L naught is suppose 5 meters. Find the strain in the rod, comma new length of the rod, and stress induced in the rod when the temperature is increased by 100 degrees centigrade. Okay. So this question is slightly tricky. So for strain, we can directly use the formula given above, alpha into delta T. So alpha is 500 by minus 3. Let's do minus 5. 500 by minus 5. Into 100. So strain will be 5 into 10 power minus 3. New length will be what? Length increase. So you have to find length increase. So delta L is L into alpha into delta T. So basically 5 into 10 power minus 3. So 25 into 10 power minus 3 meters. So new length is L naught plus delta L. So that is 5 meter plus 0.025 meters. This is 5.025 meters. Now the third part, the stress. So sigma, people will do what they will do. They will write sigma equal to E epsilon. And I've seen this many times in the answer sheets of a student. But this is wrong because the rod is free. The rod is free to expand. Thus, no stress will be induced. Thus, no stress will be induced in rod. So here the answer will be sigma equal to 0 Pascal or whatever unit they give in your option. I've seen students making this mistake a lot of time. This is very simple. If you're not constricting your rod, then there will be no stress. It will simply elongate or contract depending upon the value of alpha and delta t. So the answer will be 0 Pascal. No stress will be induced in this case. Okay. Suppose if they tell that the rod is fixed in one direction and it is free in other direction, and we are increasing giving some delta t, and they give you an alpha. In this case also the sigma will be 0 because the rod is free to expand in one direction. So still the rod can freely expand. When the expansion will happen, it will freely expand in a direction where there is no constraint. So here also sigma will be 0. This type of question, they look like very trivial, but they are asked in GATE or ESE exams regularly. Suppose if I do one thing, if I constrain the rod, if I constrain the rod properly in both directions, then there will be some induction of. Suppose if I constrain the rod like this, or if I constrain its motion along a particular direction, then there will be along the direction of elongation. Then there will be stress induction. So in this case, use sigma equal to E epsilon. So I hope I was able to like clear your doubts on this topic. Now let's do a problem which is related to this topic, but it is slightly different. So question is, a copper bar of 25 centimeter length is fixed by means of supports at its end. Supports can yield total of 0.01 centimeter. So the supports are movable and they can move maximum, okay, 0.01. So the total like delta 1 plus delta 2 of support is 0.01 centimeter. This is the yielding. If the temperature of the bar is raised by 100 degrees centigrade, then the stress induced in the bar is and they have given that alpha c equal to 20 into 10 power minus 6 per degree centigrade, and they have given EC is 10 to power 6 kg per centimeter square. So first let us write delta. This is the yielding of support. And they have given it as 0.01 centimeter. Now we will find the total free expansion. Okay, so delta free. So suppose if the rod was free, then how much it has expanded. Okay, so free expansion of rod without support, without supports. So this is alpha L delta T. So they've given L as 25 centimeter. They've given L as 25 centimeter. They've given delta T as 100 and alpha is here. So delta free is what? 20 into 10 power minus 6 into 25 into 100. So this is 50 into 10 power minus 3. So that is 0.05 centimeter. So the total so now here the total actual, so for example, what happened? Suppose this was our support, okay? Suppose this was our support. So the physics which is happening is, let us assume this was our support. And this is our rod. This is our bar. We did delta T. These supports, they moved by 0.01 mm. So suppose if here it is 25 centimeter. So now the distance between them is, this distance is 25.01 centimeter. But the rod, if these supports were not there, then the length would have been what? The length of the rod would have been. So this is the length of the rod without support. So this would have been 25.05 centimeter. Right? This is expansion. Final length after expansion without support. So essentially we can look at like this, that we have contracted the final rod to fit here. So this is the final rod and we have contracted it. So the total contraction is, so the total contraction is LF with support minus LF without support. So this is what LF with support is 25.01 centimeter minus 25.05 centimeter. So the total difference is 0.04 centimeter with a negative sign. Okay. Now, so strain is minus 0.04 upon 25 centimeter. So this is the strain. And what will be the value? Minus 1.6 into 10 to power minus 3. Now the stress induced is sigma equal to E into epsilon. So E they have given as 10 power 6 into minus 1.6 into 10 power minus 3 kg per centimeter square. Okay, so the final value of sigma is minus 1.6 into 10 power 3 kg per centimeter square. So the total stress induced is contraction. So total stress induced is contraction. Stress of value 1600 kg per centimeter square. So this was a tricky question, and I hope you were able to follow the solution. Now let's move on to another type of question from the different chapters. So question is, so they have given you a state of stress, and the state of stress is so for stress for stress for a state of plane stress on the square element ABCD, determine stresses on plane A bar by considering equilibrium of triangle portion A bar B. Okay. So in this question, let's start. They're given sigma x equal to 80 MPa. This is a tensile loading. You can see so it will be with positive sign. Sigma y is 40 MPa. The shear stress will be 20 MPa. So on positive phase, this is in the positive direction. And theta with the vertical is 90 degree minus 60 degree. So this is 30 degree. Okay. So this is so this is 30 degree theta from the vertical plane. So we can directly use the formula of stress transformation. And here we will have sigma theta equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So basically sigma theta equal to 80 plus 40 upon 2 plus 80 minus 40 upon 2 cos 60 plus tau. So if you solve this, you will get sigma theta equal to 87.32 MPa. Okay. So this is sigma theta. Now for tau theta, sigma x minus sigma y upon 2 into sine 2 theta plus minus tau xy cos 2 theta. So this is 80 minus 40 by 2 sine 60 minus 20 cos 60. So tau theta is 20 root 3 minus 1 by 2. So 10 into 0.732. 7.32. MPa in counterclockwise direction. Counterclockwise. So this is our tau theta. Anyway, so let's move on to some of the topics like beam or energy. So let's solve some problems from there. So question is, find the strain energy stored by the structure shown below. Okay, so they have given us a structure. We have also done a similar kind of problem, but that was a slightly tougher problem in our class, where I think it was in the energy class only, energy methods class. But anyway, let's have this question because these kind of question may directly come in the exams. So this is the length A and this is length L and this is C. So here the concept is similar. We have to take a section here. So we have to first consider these part BC and CA separately. So the first step is consider part BC and CA separately. Okay. And BA, sorry, BA separately. So here we have W. This is A separately. And this length is A. So first we'll analyze this BA part. So I will delete this. Suppose we make a section here, somewhere here, and we are taking x from A. So this is our W, this is A. Here the force I'm taking is like this because this is a negative thing. This is a negative phase, so the force and moment are in the negative directions, and this length is A. So if and this is the x direction. Suppose this point is O, so summation of m about O will be 0, implies that minus mx. And I'm assuming counterclockwise to be positive. So minus mx minus w into x equal to 0. So from here I get mx equal to minus wx. Oh, sorry. Because this is the x direction, so this is the positive phase now, not the negative phase. So the direction will be different. So this is v and this is our m. So here, so the convention which we are following in this course is that suppose if the phase we are considering, if the normal is in the positive direction, the forces and moments on that force we will assume as positive while doing this bending moment diagram and all. So here the cut section is along the x direction. So the normal will be positive. So we will have positive mx and vx in our free body diagram. Then we will do these analysis and we will finally get if it is actually positive or not. So from here we get that mx is wx. Okay. Mx is wx. So strain energy stored by AB is strain energy stored by AB. This is UAB equal to m square dx upon 2EI integrated over 0 to x. So EI is constant, so 1 by 2 EI will come out. And we have Wx dx 0 to A. So here we have WA square upon 4EI. Oh, sorry. Here it is mx square, so it will be Wx square. So we will have W square So this is the strain energy stored in AB. Now we will do the similar analysis for BC, and there we will find the strain energy stored. Okay. So for BC, this length is L. So let's have a cut. Now first we will have to find what is moment at B. Okay. So if we are separating this, we will have some moment at B. So at moment at B, we can find from the moment at B implies that MB, yeah, MA. This is MA basically in the formula. Put x equal to A in the formula, in the MX formula for AB. So M at B is what? W into A in counterclockwise direction. Okay. So when we separate CB from our this this structure and we take a section here, if we take suppose a section here, so what will happen is, and let's assume for CB we are having something like this. So this is our C, this is our B, and here MB is there. And this is our positive direction. This is our Y direction. So we are having a cut here. So we had a cut here. So this phase, it was the positive phase. So the opposite phase will be negative phase, right? So here the moment will be in clockwise direction. Suppose this point is P. So here My, and the load will be in the direction, and this here load will be in the negative direction. So this will be V. So anyway, so summation of moment about P equal to 0. Let's do that. So minus My plus MB equal to 0. We're assuming that counterclockwise is positive. So from here we get that My equal to MB. That is equal to W into A. So energy stored in CB is energy stored in CB equal to MCB square dy upon 2 EI 0 to L. So here it will be WA whole square upon 2EI. These are constants 0 to L into dy. So basically WA square upon 2EI into L. This is UCB. Total energy stored in the structure equal to UAB plus UCB. So that is WA cube, WA cube upon 6 EI plus WA square L upon 2 EI. So if I take WA square upon 6 EI common, so here it will be A plus 3L. So this is the total energy stored in this structure. Okay. Now I will give you a formula for impact loading, though this has been not covered in this course, but there are questions in the competitive exams which are asked from this topic directly. So impact loading. So I will give you the formula. You can remember this formula: sigma equal to P by A upon 1 plus square root of 1 plus 2AE upon PA, sorry, PL into H. So P weight starting from X, starting from rest. And so the total height weight has fallen. Before strike. A is the area of cross section of bar. L is length of bar. E is Young's modulus of bar. So the figure is something like this. Suppose we have a bar here. And there's some weight here which falls down. Suppose this falls down, okay? This is the weight of load P. It falls down by height H. And the total length of the bar is L. This is the area of cross section. And Young's modulus is given. So here we have sigma. This sigma is called sigma sudden. Sorry. Assumption is self weight is negligible. Self weight of bar basically. Self weight of bar is negligible. And this is the sigma induced in the bar. Okay. Induced in the bar due to strike. Now in this formula, suppose if H is equal to 0. If H equal to 0, load becomes sudden load. And in that case, sigma is sigma sudden equal to P by A into 1 plus, or sometimes it is called impact also, right? Due to impact. So 2P by A is our sigma sudden. And in this case, our delta is sigma sudden into L by E. Okay, this is instantaneous, also known as instantaneous elongation in bar. So let's see a few problems on this topic. maybe I will be having one problem only in this on this topic. Then we'll move on to another question. So the question is that a 50 Newton load falls through a 50 mm height onto a steel bar of dia 25 mm and length. They have given every data, I think, and length 400 mm supported on the ground. Question is, what is the instantaneous stress developed in the bar and what is change in its length? What is change in its length? Equal to 200 GPa. They've given equal to 200 GPa. So they've given each and everything. We have to just put it in the formula and we will get the value. So we can directly use, this is also called the instantaneous stress. So let's jot down all the values. P equal to 50 Newton, H equal to 0.05 meters, D equal to 25 into 10 power minus 3 meters. L equal to 0.4 meters and E equal to 200 GPa. So area is pi by 4 d square. So this will be, I will just give you the final values because the time is less. I have to cover other questions also. If you put these and you will get in, you can convert the units also, okay? So use the formula sigma equal to P by A into is 1 plus 1 plus square root of 1 plus 2AEH upon PL. So you have to understand that you can put in any units you want. Depending upon your units, you will have to convert in the end. So sigma instantaneous will become. So I will write the final value. Sigma instantaneous is 0.010186 into 1 plus square root of 490,870 MPa. So this is 71.467 ampere. This is the answer. And for delta instantaneous, use the formula sigma instantaneous into L upon E. Okay, so and delta is sigma L upon E. Delta is instantaneous displacement. So we have to put everything here, 71.467 into 400 mm by 2 into 10 power 5 megapascal. Since I am following the SI unit, I will write in SI units. And here it will be 10 power 9. So this will give me 0.142 into 10 power 5 minus 3 meters. So this is 0.142 millimeters. So this is the questions of instantaneous displacement. And these were the few topics from energy methods, or to calculate the energy, basically the energy of a structure. Okay. Now let's have one other question. Question is, a stepped shaft. Any one of you have any doubt till now? If you have any doubt, you can ask. You can write in the chat. You can unmute yourself and speak. If anyone has any doubt, you can write in the chat and you can unmute yourself and speak. Okay, it's up to you. If you have any doubt, you can ask me. A stepped shaft of brass shown in the figure is subjected to a torque which produces a total angle of twist of 3 degrees. The question part A is find torque on the shaft. And question B is strain energy stored by the shaft. Strain energy stored by the shaft. And they have given the value of G equal to 3.85 into 10 power 4 Newton per millimeter square. The figure is something like this. The diameter here is 30 mm. This is phi 1, this is phi 2 is 25 mm. The length, this length is 570 mm, and this length is 570 mm. So the total angle of twist at the free end is, so the solution. They given total angle of twist of free end. Total angle of twist of free end. So we'll convert it into radian 3 into pi by 180. So this is 3 pi by 60. Okay. This is pi by 60. So we can use formula t theta equal to T1 L1 upon GJ1 plus T2 L2 upon GJ2. This is basically theta 1, theta 1. This is theta 2. So basically theta equal to theta 1 plus theta 2. Okay, so this is what essentially is written here. So here we will replace theta by pi by 60 equal to T into 570 into 32 divided by G pi into D to the power 4. So here the diameter is 30 to the power 4. The value of G is also given, so let's replace that here by 3.85 into 10 power 4 into this plus T into 570 into 32 upon 3.85 into 10 power 4 into pi into the area here will be 20, the diameter here is 25 to 25 mm. So if you solve this, you will get T equal to 91500 Newton millimeter. In meter, if you convert, you will get 91.5 Newton meter. Okay. So this is the value of torque. This is part A. We have solved part A. Now for part B, strain energy stored equal to 1 by 2 into T into theta. So 1 by 2 into 91500 into pi by 60. This is 2395 Newton meter. Sorry, Newton millimeter. So this will be basically 2.395 joules. So in SI unit, this is 2.395 joules. So now let's discuss one of the problems from pressure vessel. Okay, pressure vessel. The question is, a thick cylinder is subjected to an internal pressure of 100 Newton per mm square. This is basically megapascal. Remember that Newton per millimeter square is megapascal. If hoop stress developed at the outer radius of the cylinder is 100 Newton per millimeter square, find the hoop stress developed at inner radius of cylinder. So in this question, they have given Pi equal to 100 Newton per mm square at R equal to Ri. Now sigma R in radial direction at R equal to Ri will be minus 100 Newton per mm square, right? Sigma at R equal to Ro is 100 Newton per mm square. So this is sigma hoop or sigma circumferential, whatever you write it, depending upon. Sometimes it is also written as sigma c. Okay, sigma c, sigma h. These are hoop stresses because they are called circumferential stresses also, right? So some people write it as sigma c. So depending upon your convention, you can write differently. Now we know that the formula. So we have to invoke the formulas for sigma hoop and sigma. So sigma hoop is basically B by R square plus A, and sigma radial is B by R square minus A. Okay. So these are two formulas which we will use. So first we do sigma R at R equal to Ri equal to minus 100 equal to B upon Ri square minus A. Then we do sigma R, sorry, sigma H at R equal to Ro equal to 100 B by Ro square my plus A. Sigma R equal to at R equal to Ro is B by Ro square minus A. So we can write sigma h at r equal to r0 will be equal to sigma r at r equal to r0 plus 2a. Now, since nothing is given in the question about external pressure, we are taking external pressure to be 0. Okay, pressure equal to 0 because nothing is mentioned about it. Mentioned about it in the question. So we get, this means that sigma r at r equal to r0 equal to 0. Okay. So we get sigma h at r equal to r0 equal to minus 100, sorry, equal to 100 equal to 0 plus 2a. So from here we get a equal to 50 Newton per mm square. Now sigma h at ri plus sigma r at r equal to ri is so here the formula will be slightly different. I made a mistake here. This will be equal to 2 times 50. So sigma h at r equal to ri is 100 plus 100, 200 Newton per mm square. Okay, so I think I made a mistake here. Let's correct it. So here minus b by ri will be there. Okay, so sigma h at r equal to r0, sigma r at r equal to r0. So there was some mistake here. Sorry for the mistake. So this will be equal to minus b by r0, sorry, b by r0 square plus a minus b by r0 square plus a. So this will cancel. So here we will have sigma h at r equal to r0 plus sigma r at r equal to r0 equal to 2a. Okay. So the formula I wrote here was wrong. That's why this happened. So from here we have total internal pressure as 0. So this is sigma h equal to r at r0 is 100. So putting the values here, we have 100 plus 0 equal to 2a. So from here we have a equal to 50 Newton per mm square. Okay. And here also we have b by ri square plus a minus b by ri square plus a. So this is 2a. So we have sigma h at r equal to ri plus minus 100 equal to 2 into 50. So here we get sigma h equal to 200 Newton per mm square. So sorry for the mistake. Actually, it happened here. I wrote the formula wrong. So correct it. I think we can take one more problem. Let's see. Let's have a beam deflection problem. Okay. So the question is, suppose we have a beam here and we load it. Suppose this is the loading in the beam. And the loading is W. The length of beam is given L. And this is a fixed beam. Find deflection at end B. So what we will have to do, we will have to cut a section. So this is our beam. And this is our loading. This unit is in Newton per meter. I will say Newton per meter. Okay. This is W. So this is the direction of X. So let's have a cut at some X. And and we will consider the right part. So this is L minus X. Here, since this is the negative, this face has negative normal, so the moment will be in clockwise direction and this shear force will be in other direction. Suppose we are taking moment about a O, so summation of M about O is 0. The total force on this beam, on this part of the beam can be approximated by a concentrated load at a length L minus X by 2 here. Okay. So L minus X by 2. The load value is W into L minus X. So basically, this is our point O, this is our moment Mx, and this is V. So, and I'm assuming counterclockwise to be positive. Minus Mx minus L minus X by 2 into W into L minus X equal to 0. So from here we get mx equal to wl minus x whole square upon 2 with a negative sign. Now this is the trivial method, and then we can use ei del 2 y by del x square equal to mx. So from here we will have e y into y prime equal to minus wl minus x square by 2 integrate over dx plus c1, and again ei into y equal to, again integrate this minus w into l minus x whole square by 2 dx. Integrate this again with some plus c1x plus c2. Put boundary conditions y prime 0 equal to 0 and y 0 equal to 0. So if we do that, we will be able to find the expression of y. Find expression of y. Yx. Then put x equal to L. So YL equal to deflection of B. The other method could be using Castigliano's theorem. If you remember what we could have done, we could have just, let's so for that, we will have to apply a dummy load at point B. Suppose we are applying a dummy load. Let us assume we applied a dummy load P at point B. So what can we do is, let's assume this is our point B, this is our point A. So we are moving in this direction. We are having a cut here. So this is W. And here we are applying a load P. P is dummy load. So the moments will be, this will be mx because now this is the positive phase and v will be in this direction. Summation of mo equal to 0. This will give us mx counterclockwise positive minus this load w can be written as wx at a distance x by 2. Okay. So wx square upon 2 minus px equal to 0. So from here we will have mx equal to wx square upon 2 plus px. And then we have to write the total energy. Write total energy. So mx square upon 2ei Then do del u by del p equal to 0 at p equal to 0. This will give you delta b. Okay. So this is how you solve this problem. Anyway, so this is how you solve this problem. I hope this session was fruitful for you. So if any one of you have any doubt, you can ask me, or I will end this session now. Does anyone have any doubt? So since none of you have any doubt, I will end this session now. Thank you for joining. This was our last session for the live session courses, week 13, I will say, the extra session actually. So thanks all for joining today. Bye bye. Have a nice day and have a great examination. Bye bye.